In this session, I will talk about multivariate process control charts and how to monitor a process mean using Hartley's T-square control chart. So that's the plan. So there are many quality characteristics in industry, all kinds of industries, where we see not just one important variable, but much more than one. So some examples are listed here. In pharmaceutical companies, people like to monitor impurity profile. And as you know, impurity is something that creates problem for quality. So monitoring that definitely is important. In semiconductor industry, where you have the PCBs used for cell phones, printed circuit boards, so they have about 200 parameters that need some kind of test. So there are so many holes to be drilled and soldering takes place. So there are over 200 parameters that need to be tested to have a good quality PCB. In chemical industry, spectroscopy produces more than 1000 variables. So if you want to monitor that, it's very difficult to do it with a single X bar R chart. And in service industry, business data are huge. So if you look at transactions and the volume of transactions that take place on a website by Amazon.com throughout the world, so that data is huge. And if they have to focus on some of the important customer related characteristics, so they need a tool. When we go to doctor and then when the doctor prescribes tests, so we have data on so many different parameters again. So multivariate quality control charts become useful when we have more than one variables. So simultaneous monitoring of multiple quality characteristics is necessary in many businesses. And somebody may say, like, if I have many variables, why not create individual control charts? So if we are monitoring mean, how about one X bar chart for each of the variables? Let's say, like, I don't have 1000 or 500, not that many, but even if I have just two quality characteristics that need monitoring, why not have X bar chart for those two? But the problem is that individual control charts can be misleading. So even in a easier and simple situation where you have only two quality characteristics, and I will show you why. So I will show you a control chart, not control chart, actually data, and they may seem in control on the individual chart. So look at this plot here. And if you look at individual charts, so this data point, which is away from this bivariate kind of data, so this data set is obviously a bit far away from the group. But if you look at one quality characteristic, it may seem all right, like this point is well within the normal limits of this variable. If you look at related data for the second variable, this one here, so once again it looks well within the limits. These points look very normal for individual variable, but together obviously you can see this is far away from the group, and same thing for this point here. So looks well within for individual variables, But on the bivariate plot, you can see it definitely looks like an outlier or out of control kind of situation. So that's why individual control charts can be misleading. So they may not give a signal of presence of any assignable causes of variability in the data when actually there is. One has to be careful. So looking further, if 99.73, like most of the control limits usually are around 99.73%. So if 99.73 of the points fall in this region, so only 0.27% is outside the limits, and follow bivariate normal points A and B, these two. May not come from the cluster in the ellipse. So this ellipse that we see, clearly it seems to be outside that band, or they are not from the same population, but they are in control on respective individual charts. So that's why we say that having an individual chart, even when you are monitoring like two characteristics at a time, so having like two separate control charts can be misleading. So what exactly is wrong with the individual charts? So now if you look at from statistical point of view, consider decision rule number one. If one variable is out of control, then system is concluded to be out of control. So even with the two, when you have like one out of control, then it is out of control. Use X bar chart for each variable, and we defined type 1 error, probability of type 1 error as alpha. So what is type 1 error? It is a rejection of true null hypothesis. So you reject a null hypothesis which is true, like there is no change in mean, but so that's the reality, but you end up saying there is a change. So that's alpha error. So type 1 error for joint control. Now if you consider both, so P is a number of independent variables using this modified alpha, because alpha is for 1. And now even if you consider a simple example where P is 4, we are monitoring 4 important quality characteristics. So it turns out that the error increases to 0.1855, more than 18% chance of committing type 1 error. So the chance of making a mistake goes up drastically from 5% to more than 18%, almost 4 times increase with 4 individual variables. If you consider decision 2 or decision rule number 2, if all variables are out of control, then the system is concluded to be out of control. Use X bar chart for each variable. We are only talking about the monitoring X bar or the average, assuming variability is in control. So let probability of type 2 error be beta. So we always represent that probability by beta. So you do the math again. So typically the standard value for alpha that we use for control limits or control charts is 0.05. So we accept that we are going to commit 5% of the time we are going to commit mistakes. So there could be a false signal. Whereas type 2 error, we accept beta as 0.1. So we are ready to accept 10% error. So note that alpha and beta cannot be simultaneously decreased. You try to reduce alpha, your beta goes up. You try to reduce beta, your alpha goes up. So you cannot like control both of them. But even if you consider the standard value of zero point 0.1 with four variables, your beta increases to 34% or 0.344. So from 10% it goes up to more than 34%. Over three times increase in committing type 2 kind of mistakes or errors. And that's huge. Like out of every three decisions you make using this control chart, one of them is a mistake or error. So that's obviously very bad. I have this data, and as you know, like we work on control charts in two phases. Phase one is where we go through the process of analyzing the data, finding the control limits. If there are any data points outside the control limit, we try to find out what is the special cause or assignable cause of that variability, and then remove that data so that our control limits are based on a process that is in control. No assignable causes of variability present, only common causes or random variability is present in the data. So what I will do is I am going to take you to Kaggle notebook. So I'm going to go to Kaggle, and under codes my work I have M10 multivariate SPC. I have already entered the codes. Just to give you a quick overview of this screen that I have. So there are things which are self-explanatory. So file, you can save anything, and you have like views and add-ons. The other thing is on the right side under settings. So if anybody works with Python, you can actually use it for Python. I'm using it for R. Under environment, if you click on preferences, I just leave it at default. And the other thing is for accelerator, if you are running a data set which is very huge and it needs a lot of power, computing power, so instead of CPU, you can even use a GPU. So it is freely available here just by switching it from none to GPU. That's very easy to do. But I'm going to basically create more room so that you just focus on what we have here. When you are running this library, so I removed the hash symbol. Hash symbol is only used for like comments or remark. You can always use that for that purpose. If you want to add any comments, it's very easy to do. Okay, so I'm going to run this line. So it will install some package which I need for this session, mainly because the data set I'm using is available in that package. So we don't have to actually read data from anywhere. And then it will use some of the libraries related to what we are doing. So QCC is a quality control chart. You can actually make all kinds of control charts. And while it is running, you will see at the top, you can see it's using CPU. Max is a 16 gigabyte. So even that one actually it is using a lot, so almost red. But we definitely do not require GPU kind of processing here. Okay, so since it is done, let's read the data and look at first 10 rows of data. So this is your data. And this data has different subgroups like 4 rows for 1, 4 rows for 2, 4 rows for 3, and so on. But this is just first 10 rows. If you look at the entire data, I'm going to just select Ryan 92 and run. This is the entire data. It goes up to 20. So there are 20 subgroups, and each with the 4 readings for first variable and 4 readings for the second variable. So that's the data we have. Before we can make a t-square chart, we have to prepare that data in certain way, and that's what I'm doing here with x1 and x2 as a matrix and saving it in XR. So if I select and run only XR, you see the data is now converted. So this is the first subgroup, then the second, then the third, and this is your first variable x1. And if you go down, same thing with variable x2, you have first subgroup, second, up to 20. So that's the kind of data we are using. And then to make a control chart, M for multivariate, QCC, quality control chart, simply run because we are using t-square control chart. So I typed t-square there. So immediately it does all the calculations. Lower control limit is 0 here, but upper control limit is slightly over 10. It also gives you more information about your data. Number of groups 20, and sample size for each variable is 4. Let's say somebody is monitoring this process every 15 minutes. So 4 data points for each of the 2 variable is collected every 15 minutes. This is based on 20. So one thing just as a caution I would suggest here is that typically for X bar R control charts, when you are only doing one variable, we say that in phase 1, when you are developing the control limits, we should have data on at least 25 subgroups. So at least. So more is always better, but at least 25 subgroups. But with multivariate control chart, this is just illustration. So I have 20, but certainly 20 is not enough for phase 1 where you are developing your control limits. So if for individual control chart, the rule is 25 subgroups of data, with the multivariate control chart, you should have even more. So that's a word of caution. Don't go by 20, that in phase 1, we always use only 20. But using this control chart, we can see subgroup number 10 here is definitely out of control. You can see it's over 60. And then the last one again shows out of control signal. So in the summary also it says number beyond limits is 2. If you do summary of that output queue, remember I saved the output in queue here. So if you just want to look at more information about the data and the control chart, it gives you something more. So summary of the group statistics: minimum, first quartile, median, mean, third quartile, maximum. Number of variables 2. Number of groups 20. We know that. And 4 is our sample size. If you find the average for x1, it is 60.37. x2 average is 18.48. And for the control limits, it also uses a covariance matrix, because when you have like 2 variables, they may be related, they may not be independent of each other. And in fact, if you look at the covariance matrix, so the diagonal, so this is like sigma 1 square, the variance for x1, and this is sigma 2 square. But then there's also off diagonal terms. So when off diagonal terms are not 0, so that definitely means that the 2 variables x1 and x2 are not independent of each other. So all the more important that we don't use like individual control charts, because these two are now related or they are not independent. So that's important. And if you calculate the determinant of this covariance matrix, so usually that is termed as a generalized variance. So it is similar to like with one variable, if you have S square, the variance. So the idea is similar to that. And then the summary also gives you the control limits, lower control limit, upper control limit. So you can get like more information about your control chart using the summary. But now let's plot the two X bar charts separately for X1 and X2 and see what happens. So if you want to make a X bar chart for X1, we have to say that the type of control chart we want is X bar, and the size, sample size for each subgroup is 4. So simply run that. It gives you a lot of information, but look at the plot. So that's your X bar control chart for first variable. So that definitely looks in control. All the data points are within the upper and lower control limits. So we cannot say that there is any assignable cause of variability present in this process when this data was collected as far as first quality characteristic is concerned. So this one, you also have all the details. So average is 60.375, so that's the central line in the middle. Standard deviation, lower control limit 37.9, so that's LCL, and upper control limit is over 80, 82.7. Number beyond limits 0, number violating runs 0. So we don't see any assignable cause of variability present by looking at this control chart. Okay. Now let's look at the second variable x2. So similar process, and it gives you this control chart. There is one point which is 1, 2, 3, 4, 5, sixth subgroup, which seems to be out of control just beyond or very close to upper control limit. But this is not the same one that we had for t-square chart. So remember, t-square had the 10th and the 20th subgroups out of control. And the chart I was looking at, x2, was indicating this to be somewhat tricky, because here we see a higher value, but it's within the limits. But 10th subgroup and 20th one are well within the limits, and x1 and x2 and x bar chart for either of them is unable to capture that out of control point that we see on t-square chart. Again, like emphasizing the need for multivariate control chart. Another plot that you can do is ellipse chart. So if I input the data or information about the control chart which is stored in Q and simply run, we can easily get the ellipse chart which is related to your t-square chart, and we are able to see this only because we have only two variables at this time. But if you have many more, obviously it's difficult to get even ellipse chart, so we have to depend on only t-square chart. So this one clearly shows 10th and 20th data points in red, and all other data points are well within the ellipse. So although this point number 6, subgroup number 6, is on the edge, towards the edge, but other subgroups are well within the ellipse. And one more thing we can notice from this ellipse chart is, if you look at x1 variable, so this variable actually, the values vary from slightly over 40 to about 80. So that's the normal range looks like. And x2 values vary mainly between around maybe slightly below 10 up to about 30. So somebody may ask a question, okay, so I have 2 points or two subgroups when this process was out of control, when the process had special causes present and that we need to investigate and remove. But which one? So should we focus on x1 or should we focus on x2? So what do we do here? So for that, again, like we may have to look at x1 and x2 and see which one is a problem. So if you look at like x2 here, the bulk of the data is between 10 and maybe I can say somewhere here between 20 and 30, you have bulk of the data. But for x1 actually bulk of the data is somewhere here, and 20 and 10 are towards the lower end of x1. So to find the special causes, like what are those causes that should be looked into and where they should be looked into, so one has to focus on x1 in that case because it's slightly towards the extremes of the lower end. But this 10th subgroup is well within the overall range of x2 and also the 20th one. So I would say one has to search for special causes in variable x1. So now in phase 1, whenever we get these out of control points, we are not done yet, because in phase 2 we have to have a control chart and limits based on the data that was in control. So what we do is we eliminate these points. Obviously we have to track what was the special cause and what action plan we should have in place whenever it is seen in future when these control charts are implemented, so that the monitoring becomes easier. And if at all at any place corrective action is needed, you have a plan ready. But for the time being, we need to eliminate them. We need to remove subgroup 10, subgroup 20, and then recalculate the control limits and see whether we have a process in control or not. So that's what we are doing here in this chunk that you see. Remove out of control points. So we are saying subgroup number 10 and subgroup number 20 we don't want. So this exclamation mark and equal basically means we don't want it. And we recreate our x1, x2 without them, and again make a plot for t-square control chart. So this is what it is going to do. And this is the outcome. So after removing 10th and 20th subgroups, you can see this subgroup number 6, which was beginning to be flagged in x2 x bar r chart, x bar chart for x2. So that is now out of control. So 1, 2, 3, 4, 5, 6th subgroup is being caught as out of control. So one point is beyond control limits and upper control limit is 11.11 now, and number of subgroups on which this chart is based is 18. So that's the situation. You again look at the ellipse. So that subgroup that was at a border actually, Subgroup number 6 is now slightly outside. Okay, so now one more iteration of removing the out of control chart in this phase. So we are still working in phase number 1, and this time I'm removing sixth subgroup and replotting Hotlink's t-square control chart. So this is the t-square chart without subgroup 6, 10, and 20. So everything is now well within the control limits. So we can safely conclude that this process is in control. We do not have any assignable causes of variability present as far as those two quality characteristics x1 and x2 are concerned. And probably we can use this to implement monitoring in phase 2. So that brings us to phase number 2. And I have this x new, which is new data that is added. So earlier data plus new data. So if you run this and look at the chart, again in this data 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So first data point, 10 data points, the process was in control. And then the mean shifted and the process seems to be out of control from this point onward. But you can see that the monitoring of the process helped to identify those out of control situations. And obviously it will not be allowed to run so long. This is like simulated data. But as soon as there is out of control point, the process usually needs to be stopped. Investigation has to be done so that it can be brought back to in control situation. So this is the example I showed you, phase 1, and then the individual ones, ellipse, after removing 10 and 20, ellipse, and then finally in control. One thing to notice is if you look at the final upper control limit here, it's 11.15. So 11.15 is the upper control limit after removing subgroups 6, 10, and 20 for in control process t-square chart. That's the limit. But if you look at phase 2 t-square chart, you may find that the upper control limit is slightly higher. And that always happens. So whenever we go from phase 1 to phase 2 limits are, we have to keep it slightly wider. I think it is done for X bar chart also when you go to phase 2. But this quality control package that I showed you does the math automatically, like how much higher it should be. So although it says UPL, upper prediction limit, but you can treat this more or less same as upper control limit. So basically it is giving a signal that the process is out of control as soon as any data point moves out, like this. But the limits are based on this data. Subgroups to the left of this red line, 1, 2, 3, 4, up to 17, because 3 were eliminated. There was a paper in 2004 by Gonzalez and Rodriguez who presented data on impurity profile for a drug, and they also did this similar thing, phase 1 study and phase 2 study. The only difference here is that we are monitoring single observation, not a subgroup. In the previous example, I had 4 observations for each subgroup. But now this is a single observations, and there were 30 different lots. So in this example, there are 5 variables and 30 rows of data. It could be 30 days or 30 batches, and these are the averages for each one: A, B, D, E, G. And then you also have the covariance matrix. So obviously these 5 variables are not independent of each other. You can see off diagonal elements have like substantial value. So all these numbers in the upper triangle is non-zero, which means that the variables are not independent of each other. And other thing you must have seen in earlier covariance matrix as well as this one is that the lower triangle and upper triangle values are likely to be same. So basically this is a mirror image. This number is same as this number. This number is same as this number. So basically the variability between B and A versus A and B, there's no difference. And for this data, the upper control limit turned out to be 12.11. And this is the plot. So in phase 1, t-square chart of drug impurities, and the lot number 8 seems to be out of control. So at that point, drug impurities are more than what is expected out of a normal process. So that eighth subgroup obviously needs to be investigated. Why impurities increased suddenly beyond the control limits? What was that special cause? So one has to investigate, use 7 tools of quality control, or do like a further data collection, investigate. Sometimes even experimentation, DOE may be needed to find like improvements. And there has to be a plan obviously for any special cause. But after removing that, we are left with 29 batches or groups, and we recalculate upper control limit. Now this time, one, two, three, fourth subgroup seems to be just out of control. What if I'm doing this phase 1, I find out of control point, we investigate and document a process or a corrective action plan so that when the charts are implemented, it can be referred to and used as an ongoing process. But how long I can do that in phase 1? So I remove one control out of control point, recalculate control limits, variability comes down, and my limits are probably narrower. Again, some point goes out. So we started with 30, and if I keep on doing this, let's say I end up removing half of the points. So obviously that's not good, and that means that process is not at this point ready for implementing SPC or control charts, and it has to be brought under control, because occasionally going something out of control and continuously going something out of control are two different things. But after removing 4 and 8, we did not have to remove anything else, and all the data points now look well within control limits. So again, in phase 2, we added some new data points beyond what we already had, and it showed some points to be out of control. And again, compared to The upper control limit in phase 1 that we ended with 11.95, the upper prediction limit 22.4 is slightly higher.
Thank you.
Thank you.
Thank you, Professor.